This is the video for homework 10, question 1. From the lecture notes, pages 1 to 50, collect the definitions and simple properties of the examples of stochastic processes. And has a list of 7 processes. The first one is the Poisson process. Poisson process is defined as follows. 1. The number n t1, t2 of the points ti in the interval t1, t2 of length t is a Poisson random variable with parameter lambda t. That is this expression. And the expectation is lambda t. The correlation is lambda squared t1, t2 plus lambda times minimum of t1, t2. And the second and third properties. The second property is that if the intervals t1, t2, and t3, t4 are non-overlapping, the random variables n t1, t2, and n t3, t4 should be independent. And the third property is that at a time point t, there is no more than one Poisson point. Using the point ti, we can form the Poisson process, xt equals n0t. The mean of the Poisson process is lambda t, which is a linear function of t. This is reasonable because the longer time we wait, the expected number of buses, any number, anything that we're waiting for. It could be buses, it could be customers entering a store, it could be cars going through a intersection, it could be calls received in a period of time. The number should be larger. The second process is the Poisson increment. It is defined as yt to be xt plus epsilon minus xt over epsilon, where xt is a Poisson process. The first order probability mass is this expression. The expectation is calculated to be lambda, and autocorrelation is ryt1, t2 to be calculated like this. When the difference between t1 and t2 is larger than epsilon, the correlation, the autocorrelation is, excuse me, the autocorrelation is lambda squared. And when the difference is smaller than epsilon, the autocorrelation is lambda squared plus this term. In the expression of autocorrelation, this term, this very complicated one, expresses a triangle with area lambda, which does not depend on epsilon. When epsilon goes to 0, the term becomes an impulse with area lambda. The third process is Poisson impulses. It is defined as zt to be a derivative of xt, or the limit of yt when epsilon goes to 0, where xt is a Poisson process and yt is a Poisson increment. The expectation is lambda, and the autocorrelation is limit of ry when epsilon goes to 0 to be this term, the expression lambda squared plus lambda times delta t1 minus t2. And this is a simple plot of it. The process zt minus lambda, we see that the expectation is lambda. So the zt minus lambda has a mean of 0, and autocorrelation of it should be lambda times delta t1 minus t2. That means zt minus lambda is a white noise, with the qt to be lambda constant. And the semi-random telegraph signal is the next process. The process is defined as follows. xt is 1 when k is even in 0.0 to t, and xt is minus 1 when k is odd in 0 to t. The first order probability masses are e to the power of negative lambda t times this and that to be respectively 1 and -1. These are hyperbolic functions. The expectation is e to the power of -2 times lambda t, and the autocorrelation is e to the power of -2 lambda times the difference between t1 t2. That is the absolute value of t1 minus t2. Okay. We can see that the probability mass when xt equals 1 is not 1/2, but when t goes to infinity, it goes to 1/2. The expectation goes to 0 when t goes to infinity, and the autocorrelation goes to 0 when t1 minus t2, that is the difference, goes to infinity. When t1 and t2 are far from each other, they become less correlated, and that is very intuitive. The fifth one is the random telegraph signal. It is defined as yt to be alpha times xt, where alpha is a random variable with probability masses of taking both 1 and -1 to be 1/2, and xt is a semi-random telegraph signal. The probability masses are the same to this, and the expectation is 0, and r is the autocorrelation is the same as the semi-random telegraph signal here. With the probability mass, it looks like a lot that the yt is a strict and stationary process because this does not change with a time shift. This is constant. And number 6, the random walk. We toss a fair coin infinite times, and it is defined as this: x and t to be ks, with k to be a number of heads, minus n minus k times s. N minus k means the number of tails. It adds up to 2k times n times s. I'm sorry, 2k minus n times s. And we say that xt equals xn times big T for t between the interval within a period. The probability masses we can tell is that this, and it calculates down to this term. And expectation is 0. Autocorrelation is the minimum of between n and m, that is corresponding to t1, t2, times s squared. The autocorrelation function contains a term, the minimum term, which comes from the probability of independent increments of the random walk. Wiener process. This is a limiting process of random walk. Wt to be limit when s goes to 0, t goes to 0, n goes to infinity of xt, where xt is a random walk. The density is, we have to calculate this first, the distribution. That goes down to 1/2 plus error function, omega over square root alpha t. And we take the derivative, we can get the density function. This is a normal density. The expectation is 0, and the autocorrelation is minimum t1, t2 times alpha. The Wiener process has an expectation of 0 and a density function in the form of normal or Gaussian function. This might indicate that in the long-term sense, which is t goes to infinity, Wiener process tends to stay at the origin point, 0, instead of wandering off.